Two neural networks. Both have 12 neurons. Both are learning the same curve. This one puts all 12 in a single layer. This one stacks them. 4 layers, 3 neurons each. Same neurons, same data, same training. One of them can't do it. The usual explanation is that deeper networks are more expressive, which is the kind of sentence that sounds like an answer. So let's watch what depth actually does. Because a network doesn't approximate a curve the way you'd guess. It folds space. Start with one neuron. It computes ReLU of Wx plus b, the max of 0 and a line. Plot it and you get a hinge, flat, then sloped, meeting at a kink. Turn up W, the slope steepens. Change B, the kink slides. That's the whole vocabulary. One neuron, one kink.
Now add them up. 3 neurons, 3 kinks, 4 straight pieces. 10 neurons, 11 pieces. And there's the ceiling for a single layer. N neurons buys you n plus 1 pieces. Every neuron you add is one more kink. Linear. Boring. So how does depth escape that? Watch these 3 neurons. 2 times ReLU of x minus 4 times ReLU of x minus a half plus 2 times ReLU of x minus 1. Add them and you get a tent. Up on the left half, down on the right. 3 neurons, 2 pieces. That's worse than before. But stop looking at it as a graph. Look at what it does to the input. Take the interval 0 to 1 and color it. Feed it through the tent. The right half comes back over the left. It's a fold. Now, feed the folded interval into another tent. Same 3 neurons, 1 layer deeper. Fold again. The crease from the first fold is still in there, so now there are 2 creases, 4 pieces. 4 creases, 8 pieces. 16. Watch the 2 numbers. Neurons go 3, 6, 9, 12, adding 3 each time. Pieces go 2, 4, 8, 16, doubling. That's the entire trick. In a single layer, neurons and pieces grow together. In a deep network, each layer folds every piece the previous layer's already made. You're not adding creases, you're multiplying them. So, 12 neurons? Flat. That's 13 pieces. Deep? 16. Not a huge gap. Push it. 30 neurons in 1 layer. 31 pieces. 30 neurons in 10 layers? 1,024. To match that 10-layer network, a single layer doesn't need 3 times the neurons. It needs 34 times. But here's the part most explanations skip. Look closely at that sawtooth. Every tooth is identical. The folds gave you 1,000 regions, and they're all copies of each other. Pure depth doesn't give you 1,000 independent knobs. It gives you 1 knob, stamped 1,000 times. Training is what breaks the symmetry. Real weights aren't the clean tent map. The creases land in different places. The pieces come out different sizes. But the exponential count survives. Which brings us back to where we started. The shallow network has 13 straight pieces to spend on this curve. It spends all of them, and it's still wrong, because 13 line segments can't bend that many times. The deep one has 16, from the same 12 neurons, and it has them because it folded the input 4 times before it ever drew a line. That's what depth is. Not more capacity, reused capacity. This is a real theorem, by the way. Montúfar and co-authors 2014, Counting Linear Regions of Deep ReLU Networks. And Telgarsky proved the separation is genuine. There are functions a deep network fits with a handful of neurons that a shallow one provably cannot, at any reasonable width. 6 lines of code. Next time, what happens when you fold the plane instead of the line? It gets strange.